This is the X-ray tube, and we know that this is what produces X-ray photons. But how do we get from the main breaker all the way to supplying the X-ray tube? And that's where the circuit comes in. The X-ray circuit can be divided into three sections: the primary, the secondary, and the filament circuit. In those, we'll also be talking about the auto transformer, a step up, and a step down transformer. Okay, so the main breaker is not only the first part of the primary circuit, but it's the first part of the entire X-ray circuit. What the main breaker does is that it, when on, supplies the X-ray circuit with 110 to 120 incoming voltage. So not only is the main breaker just for the incoming voltage, but it also works as a circuit breaker. And what a circuit breaker does is it, as in the name, it breaks the circuit in case this thing over here, the X-ray tube, tries to draw too much power. What it will do is, instead of damaging the entire circuit that you will eventually see, it will break the circuit right here. So the auto transformer has different functions, but its main function, one of the main functions, is that it takes the 110 to 120 voltage that's incoming and changes it to the 220, 240 potential difference needed to run an X-ray circuit. So that's what the auto transformer does. It also includes the KVP selector, minor and major, which are hooked up to the primary coil, and the line voltage compensator, which is hooked up to the secondary coil. The KVP major selector changes the KV plus or minus roughly 10, and the KVP minor changes the KVP plus or minus 2. And we'll prove that in the lab. What it also does is it has a line voltage compensator, which is just it regulates a constant flow of current and voltage to the entire X-ray circuit. Okay, so now that we've talked about the main breaker, the auto transformer, the KVP selectors, and the line voltage compensator, we're gonna move on to the KVP meter, which is still part of the primary circuit. The KVP meter, it's basically what it says. It measures the efficiency of the KVP that you selected with the KVP selectors. So we're gonna prove the efficiency. So the KVP meter, like I recently said, measures the efficiency of the KVP. So what is an efficient KVP range? Either it can be plus or minus 5 KVP of your original, or 10% of your original KVP. So for example, if you set to 100 KVP, the KVP meter should have a range of 100 minus 5 and 100 plus 5. So 95 to 105 is your acceptable range of KVP. So now that we discussed how the KVP meter can measure efficiency in either plus or minus 5 KVP, we'll talk about how it can measure it in plus or minus 10% of the original KVP. So let's do 100 KVP again. And 10% of that happens to be 10 KVP. So another acceptable range would be 100 minus 10, which gives you 90, or 100 plus 10, which gives you 110. So technically, your acceptable range is 90 to 110, but to be more accurate, you use the plus or minus 5, which gives you 95 to 105. So now that we've talked about the KVP meter, we're going to talk about the exposure switch and the timer circuit. The switch only initiates the exposure, and the timer circuit is what ends the exposure. So on another hand, you could say that the timer circuit is what determines how long the electrons are going to flow in the tube. So another thing the timer does is it determines the accuracy of the time selected. So what is the range that you can have that would be acceptable? Well, it's approximately 5% or 0.05, which is in decimal 5%. So say we select a second, right? So the range for that would be 1 second plus 0.05 or 1 second minus 0.05, which gives you an acceptable range of 1.05 seconds and 0.95 seconds. So now that we've gone all the way from the main breaker, the first part of the primary circuit, to the timer, which is the last part of the primary circuit, we're gonna move on to the secondary. So the first portion of the secondary circuit is the step-up transformer. It's called a step-up transformer because it takes the voltage that was supplied by the main breaker, which was then transformed into 220 to 240 voltage by the auto transformer, and it steps it up to a kilovoltage range that is used to make X-ray photons. So now that we've talked about the step-up transformer, we're going to talk about the rectifier. The rectifier simply just changes the alternating current into DC pulsating current, which is the current needed to run an X-ray tube. And also we're going to talk about the ground, which basically just prevents the radiographer from getting electrocuted from the high voltage circuit when they touch anything on the tube or anything on the operating console. Okay, so the MA meter simply just measures the current in milliamps. We talked about the secondary circuit or the high voltage circuit. We're going to talk about the filament circuit, which supplies the filament of the X-ray tube. Okay, so on your filament circuit, we start off with the MA selector. The MA selector is the amount of milliamperage that you're going to supply to your filament all the way in the tube over here. And your filament meter just simply measures that current that you selected to make sure that it's proper that goes to the filament. Next, we're going to talk about the step-down transformer, which is the last part of the filament circuit. The step-down transformer is the opposite of the step-up transformer. The amount of coils in the primary has more turns than the amount of turns in the secondary. So it takes high voltage and turns it into low voltage that's needed to supply the filament, which is over here. So now that we're in the X-ray room, here you can see the main breaker, which supplies the operating console and the tube, which is inside that dark room you can't see. But on here, you can see we have the KVP selectors, the minor and major. And when I turn the minor, you'll see that the KVP increases by about 2. Okay. Now, when I change the KVP major, it will increase by about 10. Okay. And also, you can see here we have the line voltage compensator, which is this little button right here. And when I flip this, it should show me that it's maintaining a constant voltage and current, which will push this all the way to this little red thing right here, and it should land right on it. So let's see. There you go. Also, on the operating console is your MA selector, which the lowest is 50 and your largest is 300. And this is what's going to be supplied to the filament. Over here you can see you have your timer. You could select from 1/10 of a second, 1/5 of a second, all the way to 1 second, which is the example I gave you on the board. And this determines the length of the exposure. So it stops the exposure once the amount of time has been reached. And here you have the exposure switch. This literally just initiates the exposure and does nothing else. So you have your MAS, which is your milliamperage and your seconds combined. And that is the operating console and everything that you can see from the X-ray circuit. Now, I am able to touch the MA selector and all these things because we have a ground. And I'm also able to touch the X-ray tube because of the ground that we discussed. And the ground basically just prevents us from electrification. And that is the console and main breaker. In order to see the transformers, you would have to open that up and you'd be able to see the amount of coils and turns on each transformer and whether it's a step up, step down, and the auto transformer. So now we're going to talk about the transformer law and get a little bit more in detail with each transformer. So first, in order to understand the transformer law, you have to understand what a transformer is made out of. So when we go over to the auto transformer, we have a primary wire or coil, and then a secondary coil, which all transformers have a primary and secondary coil. The thing about the auto transformer is that the transformer is in series instead of parallel. So the coils are actually stacked onto one core, or they are stacked on top of one another. The auto transformer, like I already said, has the KVP selectors and the line voltage compensator. So really the transformer law comes into place when we talk about step up and step down transformers, because it has to do with the number of turns in a primary or secondary coil. So the transformer law is N is number of turns in a coil. We have V, which is equal to the potential difference. And then we have I, which equals current. Okay, and with this, we can understand why a step-up transformer and a step-down transformer either steps up the voltage or steps down the voltage based off of these three formulas right here. We have the number of turns in the primary over the number of turns in the secondary is equal to or directly proportional to the potential difference in the primary over the potential difference in the secondary. So for an example, if in a step-up transformer, the amount of turns in the primary is less than the amount of turns in the secondary. So it would have to increase because the number of turns in a coil is also referred to as a solenoid, which is a magnetic field created when current runs through a wire or a coil. So if there's more of an electromagnetic field that's created by the solenoid, then you would have more voltage able to go to the secondary coil by mutual induction. What I didn't mention about the auto transformer is that it's ran through self-induction, which is different than the other two. So the second formula in the transformer law is the number of turns in the primary is inverse. The number of turns in the primary is inverse to the current. So it'd be N1 over N2 is equal to I2 over I1, which shows that it's inversely proportional. So now that we have these two formulas and we know that N1 is directly proportional to V1, which is the potential difference, we could say that V1, which is the potential difference in the primary, is also inversely proportional to the current. So now that we have talked about the transformer law and the different types of transformers found in the X-ray circuit, let's understand what can help or increase the electromagnetic field that's produced when a core is added to the wire or the solenoid. So this is just an air core. This would be a solenoid wrapped just in a coil. Hold on. Yeah. Okay, so this is the air core. This is the open core, which strengthens the effect of the solenoid, which is the electromagnetic field, because it has an iron core running through the middle of the wire or coil. So now we move on to a closed core, which is the most common found in X-ray circuits, because now you have closed in on the top of the coil or wire, so it creates a stronger electromagnetic field. Even though you have the same iron core running through the solenoid, it increases it because now you've closed off the top, and now it's able to facilitate mutual induction better than a open core or air core. Now we move on to a shell type, which is the last one. And this is the most efficient and best one, but it's very expensive, so it's not really used a lot. This closes off the sides of the coil as well, so the magnetic field now runs like this, and you can have your coils stacked on one single coil. So now that we've discussed the entire X-ray circuit, from the main breaker to the X-ray tube, I hope you have learned something today about the X-ray circuit, how it works, and a little bit more about how X-ray photons are produced.